in some sense, something completely different um, from what we've been doing. And in a sense, we're going to kind of go back eventually full circle to where we started the semester, right? So we started the semester with, looking at individual transistors and their function, and then what happens if you start to put a couple of them or five of them or whatever together. You can build uh, the various logic gates. And then if you start to combine logic gates in a systematic way, then you can build all the circuits that you could possibly need to have a computer. You could build a little module that does addition. You could build a little module that does the and or not, all of those sorts of things. Okay. Um, and then if you start to group those things together, then you can put together a rudimentary computer processor. And so what we're going to look at, for the basically the rest of the class is an example of a rudimentary processor. Um, and then kind of towards the end, we'll sort of zoom in yet again and look at, okay, how would we build the sort of the different actual pieces of this processor. Okay, so what we have in front of us is an extremely rudimentary and kind of for the purposes of teaching only um, computer. Okay, so this is a full-blown computer, and there are sort of if we think about a modern computer, when we took these things apart, right, you guys found the processors, you found the RAM, the memory, right? You also found a whole bunch of other things, right? So there were video cards and there were audio devices and networking and hard drives and all kinds of other stuff. Okay, so we're going to strip away all of that and just sort of concentrate on the processor and how it's going to interface with memory in order to execute programs. Um, Now, so you might say, well, okay, so if I say that this is a full-blown computer, in some sense, yes, that's true, okay? But in some sense, maybe no, it's not a full computer in the sense of usability, okay? Namely, um, how would this thing output answers to us? Or how would we put data into it, right? Uh, so it's not, in that sense, not truly a computer. Now, one of my bucket list projects is to actually build one of these damn things, um, and actually design the entire processor and maybe even get it fabricated uh, by like a, in silicon. But if not, it's simple enough. I could build it with, with a bunch of 7400 series ICs, or actually you can get chips that are programmable, so you can program what the circuit is. Those are called FPGA, field programmable gate array. That'd be probably the first place to go with this. But anyway, so input and output is and data storage is certainly something that computers need to be able to do. Um, and there's really two kinds of storage, right? There's the RAM, which is temporary storage, okay, what you're working on right now, and then there's some sort of more permanent storage, which could be your hard drive, a floppy disk, an optical drive, maybe you print something out, right? That's sort of permanent in the sense that the data stays there if you turn off the computer, right? If you print something out, the data that's on that printout is still there when and heck, even if the machine explodes, it's still there, right? Um, okay, and then you might need to put data back into it. So, what kind of input systems would a computer have besides loading things off of a floppy drive or hard drive or whatever? You've got a keyboard. Nowadays, of course, you also have a mouse. Um, some of you guys have touch screens on your computers. What other input devices are there? I guess microphones and things like that. Okay, um, so we're going to kind of ignore all of that stuff and really just look at the core function of a processor itself. and forget about the rest of that, the peripherals, okay, because they kind of complicate things. Okay, so what we have in front of us, like I said, is a very rudimentary sort of graphical representation of a very rudimentary processor. So this processor, this architecture was designed by Brookshear, who you guys probably noticed I made the book optional, right? I didn't make you guys have to buy something. It used to be required because I used to follow it a lot more closely. But anyway, he describes this, and I've written up a pretty extensive set of notes about this thing, which are linked on Canvas, assuming that I hit the right button to publish them or whatever. So we'll look at those later. Um, okay, so here's what this thing's got. We sort of want to think of two separate pieces. We've got the processor itself and the memory, okay? And now, how much memory do your computers have? So how much RAM? Yeah, gigabytes worth of the stuff, right? And even the little paltry laptops that the colleges that are sitting in here probably have between 4 and 8, somewhere in there. Okay, so gigabytes upon gigabytes of this stuff. This machine has its entirety of RAM, 256 bytes. That's it. Now, that's obviously not a whole lot, right? But it's enough that we can actually do some interesting things. And in some sense, we can visualize the entirety of the memory in this grid, okay? So the grid here is arranged in 16 rows and 16 columns. And therefore, it takes 8 bits to encode which box we're looking at in the memory, okay? 4 bits for the row and 4 bits for the column, okay? And it's arranged, like I said, here in a grid, so it makes it easy to read and easy to look at. Now, when you first sort of load this thing, which is web-based, of course, the memory has nothing in it. It's just a bunch of zeros, okay? So obviously, this isn't going to do anything if I start clicking the run button because there's no instructions, there's no data in memory. It's just a bunch of zeros. Okay, so 256 bytes of memory. That's it. Okay, and like I said, that's not a whole lot, but you could probably actually, if the architecture were slightly different, you could probably program a snake game to run in this. Okay, it really would not take that much data to have a little snake game if you had a screen. Um, okay, great. Then on the left is the processor. Okay, and all processors have little memory cells that are within them that are used for sort of the immediate things that are being computed with. Okay, these are called registers. And they're called registers actually because, well, think about like a cash register, right? It's the same kind of intent. Um, and right, so those are going to be like literally what you were doing right this instant is going to have to work within a register. Okay, so if I want to add two numbers that are sitting in memory, okay, what I have to do is copy them from memory into registers, add them in registers, and then if I wanted to put the result back out into memory, I'd have to do that as a separate process. Okay, so this is an example of what we call load store architecture because you load things from memory into a register, you do stuff with it in the register, and you put it back in memory to sort of save it. Okay, now what's different about lots of processors is how many registers you have and what they're called. Okay, this processor has a luxurious 16 of these things, okay? And, well, labeled 0 through F. Okay, that makes sense because, well, 16, right? That's how many things a hex letter can denote. So I say luxurious 16 because if we kind of go back, way back, right? So this processor would be like late 60s, maybe early 70s, kind of roughly speaking, that time frame in terms of complexity. Okay, so let's compare it to some other processors of the early 70s. Okay, so for that, let's go to the bastion of all knowledge of Western civilization. Okay, and let's start talking just a little bit of history here about the Intel 4004. Okay, this was the first commercially produced and commercially available microprocessor, meaning the whole thing was on a single chip. And there's a picture of one. Okay, you know, the size of your, you know, one of your fingernails, basically. It was not particularly fancy. And it was basically designed, at least at first, what sort of spurred it was a Japanese company called Busicom for a calculator model that they were developing. Okay, and Intel was a little smart, so they didn't just produce this processor, but they also produced sort of a range of auxiliary chips that would go with it that could interface with things like a screen or more memory or data lines to connect, you know, this device to like a printer or some other, you know, devices. So the 4004 really is sort of a series of things, but the processor itself was the 4004. Okay, and just to put this in perspective, 2250 transistors. Okay, how many transistors did it take for you guys to build the XOR gate? It was 5. Okay, 5 transistors to build the XOR gate. Okay, um, so 2250 is a lot, but in a sense, that's also not really a whole lot, right? Because that's what 500, little under 500 XOR gates worth of stuff, right? That's not that many if you think about it. Now, to put this in perspective, how many transistors are there in modern processors? Did anybody watch the I guess it was a couple weeks ago when Apple talked about their new M1 Pro and M1 Max chips. Okay, and of course Intel just released new stuff last week, I guess it was. So modern processors are on the order of billions per processor of transistors. Okay, so yeah, so you can see, of course, why modern computers are so much more powerful than old ones because, you know, we're what, like 6 or 7 orders of magnitude difference in terms of the number of transistors. So it's just a ridiculous number of these things now. So what I don't know yet is, because I haven't actually designed it yet, is how many transistors would it take to make just the CPU side of this? I'm not going to count the memory in that because that's sort of a separate thing. That's not really part of the processor. Um, I would imagine that I could probably do it with several hundred, but like I said, I'm still kind of working through the design of how to actually build one of these things. Um, okay, so the 4004, if we go to, you know, there's a lot of really interesting history here. But if we go to sort of the architecture of it, we get here, okay? So it had these as its registers, okay? It had this thing called the accumulator, which is essentially like when you start adding things together, um, then you sort of store the partial results there. And like, I mean, to think about it, if it's a calculator, right, what would you use a calculator for in the business world, right? This was, like I said, a Japanese company, right? And they weren't just making in the early 70s, they weren't making digital calculators to just hand out to school children, right? This would be a thing that sat on somebody's desk and cost a lot of money. Okay, so who would have been using these calculators? Yeah, either scientists, you know, people in academia, or people in business, right? People in accounting departments or whatever that have a crap ton of numbers that they need to add up, or whatever, right? Okay, it had index registers. It had this thing called the program counter. We'll talk about what that means in a moment. And it had this call stack, which our processor doesn't have. And but basically, what that allows you to do is subroutines and to a very limited extent recursion. Um, but if you think about a calculator, doesn't really need to do a whole bunch of recursion. So anyway, um, okay, so right. And if we compare this to, let's say, oh, I should mention actually. So the 4004 was the first commercially available microprocessor. And I'm going to put the emphasis on the commercially available because it wasn't the first microprocessor. But nobody knew that until the 1990s. Because the first true microprocessor was, well, why would we not know about it until the 1990s if it existed in the early 70s? No, definitely knew that it was a microprocessor. Yeah, it was classified. Okay, so the first microprocessor was actually developed to be part of the flight computer system for the F14 Tomcat. Uh, and now, how many of you guys know the F14? Yeah? What movie is Top Gun personifies the F14? Actually, I was just thinking about this last night because I went to B-Dubs with the wife for dinner. Um, and actually, okay, let's make sure that we're all on the same page here. Am I actually married? No, most certainly not. And if I were, would I be married to a lady? Most certainly not. Okay. Uh, so no, a joke that got started a long time ago is that Professor Geldman and I are married. We were at a fraternity dinner, and we were sitting with a freshman that we both like knew his name, but we didn't know him really well. And that's the whole point of fraternity dinners is to get to know guys. And so I get up to go get dessert or something, and he leans over and she's like, or to her, and it's like, so what's it like being married to a math professor? And it's like, oh honey, oh child, you have missed all of the memos. Um, anyway, so since then we've kind of joked that we're husband and wife. So anyway, so we went to B Dubs for dinner last night, and Highway to the Danger Zone comes on the music, right? And the second you hear that, right, you instantly think Top Gun, right? Because the song was actually written for the movie, um, which I didn't realize until last night. I thought that they just picked it because it fit, but yeah. Anyway, so you guys have all seen that movie, right? You've not seen Top Gun? Oh my God, child. What is wrong with you? Okay, you have an assignment this, well, okay, maybe not this weekend. You guys are, okay. That's true. He's got a, yeah, where are we on all the Star Trek, by the way? Yeah, you got a lot of work. I don't think it's even possible now to get through it in the number of hours remaining in the semester. So, yeah. Okay, so anyway, the F-14 was an interesting aircraft because what could it do with its wings that was sort of, yeah, its wings could actually move, right? So they could be out for lower speed and they could retract back for higher speed flight, okay? And this, as you could imagine, is a pretty complicated, I mean, even mechanically, it's pretty complicated, but calculating like how should you, how should the control surfaces move and how should the engine respond and when do you even bend, move the wings? All of that stuff needs to be controlled by a computer. And so the first processor was actually developed for that project. And it then ended up getting used on even, I think, the early space shuttle prototypes. Because they already had this thing designed, might as well reuse it. But it was super classified until like the 90s or something. Um, and so there's really not a whole ton of information about it out there. Anyway, okay, so Another processor of the 70s era, and this is my favorite. Owen's probably sick of me here talking about it. Okay, so mid 70s is the 6502. Okay, now you guys have probably never heard of the 6502 unless I've mentioned it, but you've definitely heard of, and it had on the order of 3,000 transistors if memory serves. You've never heard of the 6502 by name, but you have definitely heard of all of the computers that have used it, including the Apple II, okay, the Atari line of video game and computers, right? The Commodore line of video games and computers, and a bunch of other game consoles, including these two, right? Or which really is one, okay? So the Famicom and the NES, the Famicom was the Japanese sort of release, and then they kind of redid it for an American audience and released that as the Nintendo Entertainment System, but also the Tamagotchi, right? Now, I'm sure nobody in this room would admit to having had, I don't know, but maybe some of your sisters did. No? You had one? Yeah? You did? Hmm? Yeah. Okay. So yeah, the Tamagotchi actually used this thing, or sort of a variant of it that was super low power. And actually two fictional characters have used this. The T-800 Terminator series, okay, and Bender from Futurama. Okay, so there's an episode where Bender gets X-rayed and you see his brain, and there's a little box and it says 6502 on it. Okay, so it's one of those little in jokes that the writers of Futurama kind of threw into the to basically amuse nerds like me who would notice that sort of thing. Okay, uh, and the T-800 Terminator series. So how many of you guys have seen like Terminator 2, right? So you know when you've not seen Terminator 2. Uh, yeah, but these are like oh child. Yeah, look at you using big words like wavelength. Yeah. Oh, Lord, child. Um, okay, so yeah, so in Terminator 2, there's some of the scenes where you're sort of seeing through the Terminator's perspective, and there's like red stuff, and it looks all computery, robot-y, but there's code kind of running down the side. That's actually code for a 6502. Okay, which is just kind of, huh? Well, okay, so it's not just because I'm a giant nerd that I know that. Okay. Um, the 6502 is a really interesting processor. The history of it is really interesting. And look at all of these machines. Like I mean, maybe I need to put this in perspective, right? But the Apple II and the Commodore PET were two of the three computers that were released commercially in 1977. The other was the TRS-80. Okay, that basically that year, 1977, is what we call the Trinity, because these three machines came out. They were commercially available. They were expensive by today's standards. Okay, you definitely had to be upper middle class to afford one of these, or a college or something, to afford one of these things. Okay, um, and but they spawned sort of the personal computer revolution. Okay, And the success of those led to these other machines, including this one, the Commodore 64. That was the first computer I ever used, okay, when I was a child. And we had that thing into the early 90s, if memory serves. It was freaking amazing. It had 64 kilobytes of RAM, right? But, you know, my family could afford a computer. I think my dad bought it in 1983 or 4. The Commodore 64 came out in 82. And, you know, he wasn't making a ton of money. He was a Marine, you know, first lieutenant at the time. Um, and he had a wife and, well, me. Okay. So, yeah, so it's machines like that that spawned the personal computer revolution, of course, and then you get the things like the Nintendo, and well, you guys know the gaming side of the history, but the processor that's in both of these things is almost identical. Okay, so the other reason, Kiani, that I know all of this is because next semester I'm teaching an advanced course for the CS majors on programming the Commodore 64 and the 8-bit Nintendo. Okay. So, yeah, so I obviously need to know a lot of the technical details to do such a course. Um, okay, anyway, so this processor had, uh, here we go. This were its registers. It basically had 3 of them, okay? And 2 that were used for indexing, and 1, the accumulator, is basically where all the arithmetic went. But you had a bunch of memory, and so you could store things out in memory. Not a whole lot to work with. So having 16 of these registers, you guys will find is luxurious, but eventually you run out of them and you have to start using memory. Okay, so let's go back to our processor for the sake of, well, and actually I want to go to Canvas because I want to pull up my notes now. Once it decides to load, of course. You guys all been registering for classes? No? Which one? Which one? 271? No. Uh, Cody, you would not have a good time, my friends. Well, that's certainly one solution to it. Okay, where the heck did I put this? Okay, I don't think I've put it on our course Canvas page. So let me go back to last year. Okay, here we go. Okay, so this is going to take a second to load, and I'll put a link to this on Canvas after class. So, so I've written some pretty extensive notes about this that go into a lot more detail than the book does. Um, and this Pi is really slow today. So this file lives in Dropbox, and I link to the actual version of it. So as I update it, it sort of is live on the internet. Okay, so we'll talk about this decoder stuff later because that's still a work in progress. Okay, you know what? I'm gonna download this because this is too damn slow trying to load it live. Okay, you know what? Let's kill this. Oops. And I'm sorry, this is taking a minute. Okay, so what I'm basically going to load here is what the instruction set is for this thing. So, you know, what kind of instructions would you want a computer to be able to do? Hmm? Like very simple instructions. Right, add. Okay, subtract would be nice. Um, you'd like it to be able to do the logical operations like and, or, and not. Okay, you'd like it to be able to, well, if we've got memory, we need an instruction to put something from a register out to memory. We need another instruction to take a number from memory, put it into a register. We need another instruction to, like, let's say, put a particular number of our choosing into a register. We need an instruction to be able to move data between one register and another. We need some sort of arithmetic instruction, so addition. We need the logical instructions like and, or, and not, and XOR, and that sort of stuff. Okay. And if all we have are those, okay, we don't have a computer. Okay. The most important instruction that makes a computer is a conditional instruction, right? So in Python, or when I had you guys fold pieces of paper or whatever, right? Whenever we say the word if, we're checking something. Is this less than that? Is it equal to it? Something, right? And whether or not a piece of an instruction gets executed depends on the result of that if statement, right? So we have to do a logical check. So we need one of those too, okay, in order to okay, so this will hopefully be faster because it's loading it off the machine instead of the web. Oh, much better. Okay. And if we start to add those up, that sounds like not very many instructions, but it also gets to be quite a pile of them. So here are the instructions that this machine has as its, yeah. So let's sort of look at the description table first, and then we'll worry about all this gobbledygook to the left of it, okay? So here are all 12 of the instructions that this machine can do. Now, 12 may not sound like a lot, but as you will find out, it actually is enough to do things. So what do we got? What are the first four, basically? Okay, we're able to take data from memory and put it into a register. We're able to take specific numbers and put them into registers. We're able to take data from a register and put it out to memory. and we're able to take data that's in one register and copy it over to a different one. Okay, so those first 4 instructions are all about moving data from one place to another. Okay, good? All right. The next 2, or next, I guess, 8 instructions, okay, are arithmetic or logical. So the book that, of course, I got this from actually defines 2 different types of addition, one for integers and one for floats. Okay, and you guys wonder why I taught you guys 8-bit float stuff? It's because that's what this machine uses. With one minor caveat, I taught you guys slightly different than the way the book did it, but because the way the book did it was stupid. Okay, but we can do addition. Okay, then we've got OR, AND, and XOR, and those work bitwise. We'll talk about this more later. And then we've also got this thing called rotating. So rotating a bit pattern is, well, it's kind of like shifting bits, right? So what was the, and I know I've told you guys this story, when I used to work at Kohl's and somebody came up after Christmas and was like, how much off is all of this? And what did I do? Yeah, I moved the decimal point, but that's equivalent to shifting the digits and leaving the decimal point where it was and just shifting the digits relative to it, okay? So shifting bits, okay, or rotating bits, and there is a slight distinction between those two, is one of the things that's on our menu, okay? All right, the next instruction, the jump one, that's the key instruction that makes all the magic work, because it allows us to do conditional expressions and then also do loops, okay? And then there's an instruction that basically says stop doing stuff, okay, so a halt. That's the very last instruction, of course, that any program should execute because, well, when you're finished, you should be sort of finished. Okay. What's missing out of this list? It's only 12 of them. What else would you maybe like to have had? Okay, so Mr. Koch, what was one you mentioned? We've got add, but we don't have subtract. Does that seem like an oversight? I mean, it'd be nice to have it, right? But is it necessary to have it? No. Okay. And the reason is, how do we do subtraction? You add its 2's complement, right? Well, how do you get its 2's complement? You flip all the bits and add 1. Okay, well, we can do the add 1 part for sure because we've got addition. Can we do the flip all the bits? Yes. If we're clever, we can do that with the XOR command, and we'll look at how to do that later. Okay, so while it would be nice for there to be a single instruction to do subtraction, we don't really need it because we can build it out of several other instructions. Okay, so having a subtraction operation would be mere convenience. Okay, all right, what else might be nice if it were in the list? Like, let's say I was building a rudimentary calculator out of this thing. Yeah, wouldn't multiplication be great? As a single instruction? Oh yeah, that'd be wonderful. Guess what? You don't have it though. Okay, so here's a much bigger question. Is it possible, using the stuff on that list, to program multiplication? Now the answer, of course, is yes, because I wouldn't ask the question otherwise. Okay. How do you multiply numbers? Yeah. Okay, that would certainly work. That's a relatively inefficient way of doing it, but it certainly works, right? So if I want to do 5 times 7, okay, what could I do? Add 5 to itself 7 times, and eventually, it would take me a little while, but eventually I'd get 35. Okay, so that certainly works, right? if we can do addition and we can do some sort of loops, we could totally go that way, okay? Now, would you guys agree, though, that that's probably a pretty silly way to do addition? I mean, multiplication. Yeah, okay. In particular, what happens if I give you like really big numbers and I say, I want you to do 1832 times the weight of Cody's mother in kilograms? Okay, huh? Yeah, it would take, you know, infinity number of operations, right? Uh, yeah, that would make me a very happy panda, Cody. So, all right, anyway, so point being, if you had really big numbers, okay, that approach is clearly not going to work, right? It would because it would take, you know, doing a loop thousands upon thousands of times, and that's just not realistic, okay? So we have to kind of go back to the drawing board and think about, well, how did you guys learn multiplication back in school, right? So if I wanted to multiply, oh, I don't know, 32 times 17, and I'm just making up numbers here, how did you guys learn to do this? Right, okay, so what you did, right, in school, you said, okay, 7 times 2 is 14, carry the 1. 7 times 3 is 21, plus 1 is 22. Shift, because I'm now looking at something in the tens place, and 1 times everybody is just itself, and then you add the partial results, and there we go, right? Okay, that actually is not the way that the optimal way to do it on the computer. Okay, let me show you another way, and this one's going to blow y'all's minds. Okay, I'm going to write the numbers in 2 rows like that. Okay, on the left, I'm going to, hold on, which way do I want to do this? Hold on 1 second, let me just double check. Mr. Pandoli, my wife has texted me. You need to register for classes. Okay. Okay, it's the halves one that you cross out, right? Okay. So what I'm going to do is I'm going to take the first number and I'm going to continually double it. Okay, so what's double of 17? 34. Okay, and what's half of 32? 16. Okay, what's double of 34? 68. What's half of 16? Okay, and then this one is obvious, right? Okay. Then 68, what's double that? 136, okay. What's double that? 272. And then what's double, or well, actually we won't need that, but what is double that? It'd be, okay. Yeah, it happens to be 544 here, okay. But, so what I'm gonna do though, is I'm gonna look at my numbers here, and I'm gonna cross out any row that has an odd number over there on the halving side, okay? I'm going to then take the remaining numbers and add them. So what would happen if you added 17, 34, 68, 136, and 272? So sit down and do that real quick, or bust out the calculator. Okay, me using 32 for one of the numbers was not a good example. I'll do another one in a second. So what is it? Huh? You sure you got all of them? All right, let me just double check that I'm not being an idiot here. 17 plus 34 plus 68 plus 136 plus 272. 527. Where's the other? Uh, oh, okay, hold on. Maybe I'm being an idiot here. Oh, it's because I crossed out the wrong thing. Cross out all the even ones, not the odd ones. Okay, so if I crossed out these and then look at the doubling side, what's left, in this case, it's only a single number. This is why 32 was a bad example. So let's do 31 times 17, and I think it'll actually illustrate it better. Okay. Okay, so let's do it again. So 17, 31. All right, we already know what all the doubles are, so I can just copy those down. Okay, and I'm not going to do the last one. Well, we'll keep going. All right, so what's half of 31? You know, this is actually an interesting question because what should the answer be? 15.5. Okay, but when I say half, I'm going to discard any remainder, right? So you guys remember when you did division in elementary school, like third, fourth grade, and you said the answer was something remained or something? Okay, uh, just ignore the remainder. Okay, so if I did that, what would be 31 divided by 2? 15. Okay, all right. Then if I divide that by 2, I get 7, right? So I'm discarding the remainder each time. If I divide 7 by 2, I get 3. If I divide 3 by 2, I get 1. Okay, this is actually maybe also a bad example because every one of those numbers is odd. Okay, so if I cross out the ones where these guys are even, there's nothing to cross out here. What's 17 plus 34 plus 68 plus 136 plus 272? Huh? Which is 17 times 31. And double check that. Huh? Mind blown? Okay, did anybody learn this particular method of multiplication in school? I highly doubt it. I didn't actually learn this technique until graduate school. Okay. And at the time, I thought it was stupid. Okay. So now, where I ran across this in graduate school was there was one of the professors that in the math department that he was half in the math department and half in the math ed department. Okay. That trained the math ed majors were students that wanted to go on and basically be math teachers in middle and high school. Okay. Okay, so fine. But he taught a course that was like math for elementary school teachers that would be intended for the students that were wanting to go on to become elementary school teachers. And he taught this technique. It's called the Russian peasant method. Okay. And at the time, I thought, this is the silliest thing I have ever heard of. Why would you ever want to do this? Like, get off my lawn. What's wrong with the way that everybody has been multiplying since the dawn of time? Right? But it turns out, and it wasn't until I was a professor here that it finally dawned on me, this method is actually really useful for teaching, for programming a computer to do multiplication. And it's really great in binary. So what do you think you guys might be doing for a project? A different project. Yes, program Russian peasant method multiplication in Minecraft. Okay, that I would be impressed if you could pull that off. So anyway, all right, we will continue with this exciting journey. And how are speaking of Minecraft, how are the lessons coming? Cody, they're going excellent, aren't they? Yeah? Okay. All right. See you guys on Friday. Oh, and before I quit the stream and before you all walk out the door, Are we all clear on retake instructions on Friday? Basically, what do? Come to my office. I'll give it to you. Go find a quiet place. Bring it back. I know you guys all have different schedules, so I'm going to kind of chain myself to my desk that day. And you can kind of come by anytime. Obviously, you guys know you'll need basically 45, 50 minutes to do it. So don't come 10 minutes before you have to be at another class, right? Don't be a dumbass. And let's hope that we're getting like 8s and 9s and 10s out of 10. That would make me so happy, Cody. It would make me a very happy panda. And I would, if you manage to get a 10 out of 10 this week, if you give me a glamour shot of your mother, okay, I will frame it and put it on my nightstand. Okay, we'll do 2 of them. Yeah, that sounds great.